Good afternoon, everyone. Welcome to this celebration of the life and career of Bob Sinsheimer. I'm Stephen Poole. I'm chair of MCDB at UCSB, and I met Bob when I first came on campus as an assistant professor almost 30 years ago, and we've been friends ever since. For most of that 28 or so years, we had lunch together every day, and Bob was, it was almost the highlight of my day to go to lunch with him all those years. He had an intense curiosity about everything from sports, Dodgers. We lamented about the 49ers for the last, I can't remember the last time we didn't. To history and politics. I don't know if you know that for one of their vacations, he and his wife drove around the United States visiting presidential libraries. I mean, that's an interesting vacation. But above all, Bob was really curious about science and its ability to inform our view of the world. This curiosity was a hallmark of his entire career. He was one of the founders of the field of what we now call molecular biology, which revolutionized biology in almost the same way that quantum mechanics revolutionized physics. And this curiosity served him well through his career at Caltech, through his shepherding of UC Santa Cruz as chancellor, and for the many years he joined us here at UCSB. So again, thank you for joining us here. Moshe Eisenberg asked that I say that he sends his regrets. He planned to be here, but he had a personal emergency that he could not get here from. All right, so first off, I'd like to introduce Roger Sinsheimer, Bob's son.
Good afternoon. I'm sort of sorry to be here with all of you in the sense that he would have loved to have been here. He would have loved to have seen all of you together and to have shared this time with you. Unfortunately, he cannot. So let me see if I can give you a recap of what's happened. Let's start at the end and then wend our way back to the beginning and then fill in the middle. Dad had been suffering from competing organ failures for the last couple of years. First his heart, then his kidneys, then his heart. They were in a race to the bottom, but he and his doctors kept beating them into a few more months, a few more weeks, and then I was with Dad beginning 3 days before he died. He had gone down this last hill very quickly. 12 days before he passed, he was at the gym working out with his trainer, Mike. Things were looking particularly dire that week. We had called in hospice. Dad had gotten to a point that he could no longer walk without assistance. His assertion was that he had a particularly nasty bug. He would beat it, and we'd be back to where he had been, if not better than ever. This was a fellow who had magazine subscriptions out to the year 2020. He had no intention of going anywhere. The morning before Dad died, I sat down in the living room with the hospice nurse for an update after she had checked him out. I was stunned when she asked me if anyone had talked to Dad about the fact that he was dying. I had to admit that I had not, that I knew that he was very sick, but had not yet resigned myself to that outcome. The nurse suggested that someone, not that there was any of his other children there, so she meant me, needed to tell him that he was going to die. This was not a conversation I wanted to have with anyone, least of all my father, but it looked like it was time to stand up and do it. I went into his bedroom where he was lying, breathing raggedly, and put my hand on his leg to rouse him. I said, "Dad?" He'd been more and more incoherent over the past 24 hours, so I wasn't sure that he'd respond. He nodded his head weakly. I said, "Dad, this is not looking good. You are not just sick, you are dying." He opened his eyes, something he was doing less and less, and looked straight at me. He roused himself up a bit, pursed his lips, and said clearly, "I refuse." Then settled back into his pillow, satisfied with himself. Here he was at the end, cracking wise. I responded that I knew that this was not the outcome he wanted, that he had fought more than anyone to continue to live, that we did not want this for him, but it looked like he had run out of miracles. He sighed, sank further back into his pillow, and appeared to nod off. Occasionally, he'd quietly say, "Wow." Other than those exclamations, his stated refusal to accept death were his last words. He passed early the following morning. It is popular to say of the dearly departed that he broke the mold. In Dad's case, there was no mold. He was the son of a magazine journalist from Chicago and a pharmacist's daughter from New York City. These two were wonderful, successful people, but had no comprehension of the path that their second son was going to embark on. One of Dad's great disappointments in life was that they never really understood what it was that he was accomplishing. Dad was born in 1920 in Washington, D.C. The family shortly thereafter moved to Chicago, where my grandfather had grown up. The apartment building where his family lived back then is long gone, just southwest of what is now the Magnificent Mile, for those of you who know Chicago, not far from the river. Dad would tell of the bitter cold he had to endure to get to school, having to walk across a bridge over the Chicago River in the dead of winter, with those infamous Chicago winds howling and blowing snow at him. He would hide in the lee of a building, then dash across to the protection of a building on the other side, then continue his journey to school, shivering from the cold. But off to school he went with a vengeance. In high school, he was all-city chess champion, as any of you bold enough to try to take him on at chess can certainly attest. He was determined to go to an elite East Coast university, but his parents could not afford it in the midst of the Depression. So he worked hard in school and got a full ride to MIT. His parents still did not want him to go. It was only through brute stubbornness that he went anyway. His 6 years elder brother, Alan Jr., the lawyer, had gone to the University of Chicago, and that's where his parents wanted him to go as well. As you may have encountered, he learned a powerful lesson during this time. Stubbornness was one of his signature traits, one that he felt held him in good stead throughout his life. At MIT, he excelled in math to such an extent that a letter was written to his teachers back in Chicago commending them for having prepared him so well. I have a copy of that letter. His roommate, Arthur Graham, was studying aerodynamics. One time Art was stumped at a homework problem. Dad said, "Let me take a look at that," and quickly knocked it out. From his point of view, it was just math, even though the problem was in the field that he was not studying. One thing he never did excel at was doing his own laundry. His parents had a special trunk made, and he shipped his laundry back to Chicago by train to have it washed by the maid and returned to him in Boston. He did outstanding work in school. After 4 years at MIT, he received both his bachelor's and master's degrees simultaneously and was invited to stay to complete his PhD at MIT. World War II intervened, and he spent the war years working in the RAD lab at MIT, helping create a short wavelength radar system that could see through clouds, one that was light and compact enough to be mounted inside of bombers. He flew inside the rear of B-17s, lamb's wool jacket and all, to test the radar and report back that they were succeeding. The radar they designed was not deployed during the war, but what they accomplished back in the dawn of electronics was truly astonishing. Again, it was just math. Not too shabby for a fellow with degrees in biophysics and biological engineering. He went on to earn his PhD in biophysics in 1948, one of, if not the first PhD in that discipline. While doing all this, he met my mother in Chicago, wooed her, and married her in 1943. My mom's father was incredibly impressed that Dad was a scientist. He thought Dad was a real catch. Mom's parents, as with Dad's, had seen the seeming miracles that had been created by science during their lifetimes. Dad's grandfather, my great-grandfather, was a merchant. His father, a journalist who had reported on the Silicon Valley of their day, Detroit. When Dad was born, they were living in Washington, D.C. They had moved there so my grandfather could report on the military's transition from cavalry to mechanized warfare during the Great War, what we now call World War I. My grandparents had seen the world's transition from gaslight to electric light, from the icebox to the electric refrigerator, the horse and buggy to the automobile, the telegraph to the telephone, the orchestra to the record player, and then to the radio, from birds to airplanes. Science had created all these miracles right before their eyes. They wanted more and respected the heck out of their heroes of their day. Henry Ford, the Dodge brothers, Bill Durant, the founder of GM, Walter P. Chrysler, Ransom Olds, Lewis Chevrolet, Charles Nash, all of whom my grandfather met during his reporting career, and the pantheon of other famous scientists and technologists from the early 20th century. After MIT, Dad moved on to do his postdoc work at the Iowa State College in Ames as an assistant professor in the physics department. He was then recruited by Max Delbruck to come to Caltech in Pasadena in 1957. He chose to study the tobacco mosaic and the FX174 viruses. He became an expert on both of these. In the mid-1960s, he partnered with Arthur Kornberg and Mehran Gulian to build a FX174 virus. For this last work, he was named California Scientist of the Year in 1968 and was recipient of the 1969 Bioink Virology Medal. Before I review Dad's career in greater detail, I should mention that he told me many times that 10 years was enough of doing one thing. As you'll see, his actions certainly followed his words. In 1938, Dad began his undergrad work at MIT. In 1942, he received simultaneous degrees of Bachelor of Science in Biophysics and Master of Science in Biological Engineering. This unusual simultaneity of degrees presumably had something to do with the beginning of World War II 6 months earlier. That said, a master's degree after 4 years of school is quite the accomplishment. He immediately started work at the Rad Lab after his graduation. Now it's 1948. He received his Doctor of Philosophy, and I'll read the entire title that's on his degree, in recognition of his scientific attainments and ability to carry on original research as demonstrated by a thesis in the field of biophysics entitled Development of Methods of Microspectroscopy and Low-Temperature Spectroscopy for Biological Research. Again, he received his PhD in record time, considering that he had spent 3 out of the intervening 6 years working at the Rad Lab. I should mention that Dad met a researcher in the 1960s who told him that he'd been doing work in the area of low-temperature spectroscopy, and that Dad's thesis was the leaping-off point for this gentleman's industrial work 15 years later, as no more definitive work had been done in the area in the intervening years. In 1949, he started his postdoc work at Iowa State College. Dad presumably was thrown off his 10-year plan just a bit, 1 whole year, by his World War II stint at the Rad Lab. 1957, he was recruited to Caltech by Max Delbruck. 1968, he became chairman of the Caltech Biology Department. 1977, became chancellor at UCSC. 1987, he retired to Santa Barbara, became a professor emeritus at UCSB. And in 2017, he passed away after 30 years of retirement. I put quotes around retirement because, as you all know, he was a very busy man. While he was doing all the above, he became renowned as a microbiology ethicist, and for the 1985 meeting he organized at UCSC that ultimately resulted in the Human Genome Project. He was a big supporter of the William M. Keck Observatory in Hawaii and was instrumental in finding the funding for that effort. In 1967, he was invited to join the National Academy of Science, something he was incredibly proud of, an institution he strongly supported for the rest of his life. As chancellor of UCSC, he laid the path for the university to grow from a small overflow school to a major power in the academic world, creating many university industry tie-ins. It took him 3 tries to find a woman who could match him in the stubbornness department. I'm sure many of you have fond memories of Karen, who passed away in 2015 from pancreatic cancer. He will be remembered by many as the mentor who greatly challenged them, but at the same time drove them to learn immense amounts under his tutelage. The students and colleagues who worked in his labs, and his peers. He will be missed. I want to acknowledge his friends and colleagues here in Santa Barbara, Tom Harriman, Stephen Poole, and many others with whom he collaborated and had fun. I especially want to acknowledge my sister Kathy, who tirelessly visited and supported Dad from her home base in Oakland, especially in these last few especially difficult years. All of you here today, and those who could not be here but are here in spirit, thank you for being his friend.
Six months after Pearl Harbor, I landed at MIT and was taken under Arthur Graham's wing. I didn't know a damn thing about aviation, and Arthur got me through the whole works. Bob and Arthur were roommates at MIT, and so they are my longest, oldest friends to this day. And I'm afraid that they're outclassing everybody else. Anyway, they compliment me by calling it a triumvirate, and I don't rate their powers at all, but it's nice to try. To me, one of the strange things about life is that World War II changed my career, and I think it helped Bob's in the sense that the radar lab experience made an instrumentation electronics engineer out of him. And that's a key part of the development of the Human Genome Initiative, which is to come later. Arthur Graham would say, and I'll borrow his phrase, if he were here, he can't travel anymore. Bob's work overall puts him in the absolute top rung of scientists. He was my guru for everything involved in bioscience.
Hello again. I'd like to just talk briefly now about the early aspects of Bob's scientific career. As Roger said, he grew up in Chicago, was an outstanding student in Chicago, and was able to earn a scholarship to MIT. He had an interest in chemistry. His father didn't really think he should go into chemistry, but chemical engineering was okay. So when he went to MIT, that was what he was going to start out as, is chemical engineering. The first 2 years at MIT, all students took the same classes. They all took 2 years of physics, 2 years of math, 2 years of chemistry. And during that time, Bob started to realize that chemistry really was not exactly where he wanted to be. There was something in the air about nucleic acids, and he just thought that was kind of interesting. Fortunately for him, right around this time, MIT, which had previously had a very anemic biology program centered around sanitary engineering, decided that this was not appropriate for MIT, and they completely revamped and made a new program appropriate for MIT in biophysics, centered around biophysics and biochemistry. And Bob decided he wanted to switch into that. There were very few faculty initially, so Bob had to take courses in a wide variety of areas, took courses in circuit design, engineering, UV spectroscopy, all sorts of things. And these served him very well for the rest of his career. And the UV spectroscopy course was with John Loofborough. Hope I got that name right. He was a UV spectroscopist, and so Bob joined his lab using just trying to develop methods to use UV spectroscopy to look at purines and pyrimidines. As you know, after Pearl Harbor, John Loughborough was recruited to the rad lab at MIT, and because Bob had excelled in his courses in circuit engineering, Loughborough recruited him as well to the rad lab project. And that was, as Roger said, they were trying to develop ways to be able to detect air-to-air and air-to-ground things with the newly invented magnetron. And Bob said that he did a lot of flying, and he got airsick in every single flight that he took. He also managed to get through several very harrowing crashes. All right, so after that, when he returned to MIT for his PhD, he stayed in the Loughborough lab, and he was intensely interested in DNA at that point. So during the war, some experiments had been done that had pretty definitively shown that the nucleic acids were the genetic material. Most people had assumed that proteins were going to be the genetic material because proteins were complex, nucleic acids were very, very simple. But experiments done sort of during the war years showed that nucleic acids were the genetic material. Many, many scientists were not convinced by these experiments, but Bob was. And so he decided he wanted to be studying nucleic acids. And so his PhD thesis was to develop methods in UV spectroscopy to study nucleic acids. Part of this was developing a UV microscope to be able to get spectroscopic data on small regions of cells. And right here is Bob's first paper, Christensen filters for the ultraviolet. It's a very clever method of developing filters for doing this UV analysis with the microscope. So then, following his PhD, Bob was able to get a position in the physics department at Iowa State. He had a choice between Wash University, St. Louis, and Iowa State. And at the time, Wash University was kind of a podunk little place, and Iowa State had a physics department that was interested in biophysics, and that's where he went. He wanted to continue his biophysical studies and wanted to study the properties of the components of DNA, nucleotides. Now, nowadays, you know, even when I started graduate school, we could just buy biochemicals. Nowadays, you don't buy biochemicals, you just buy a kit to do all your experiments for you. But back then, there was nothing like that around. And so his first few years at Iowa State were there to figure out how to produce nucleotides from calf thymus DNA. And let's see, there it is. This is his first paper from Iowa. He not only developed ways of generating mononucleotides, the basic components of DNA, but then separating them. So those different peaks that you see are the different bases of DNA separated. He also found that methylcytosine was a component of mammalian DNA, which I don't think people had known before that. Okay. So he published a series of very elegant studies on mono and dinucleotides, but he really wanted to get beyond the test tube. And Bob, even back then, was thinking that, here's this paper, First Steps Towards the Genetic Chemistry. So genetics had been around prior to this, but he wanted to be able to use the techniques of biochemistry and biophysics to really understand what was going on with the genetic material. And so one of the ways he decided to do that was to get beyond the test tube and look at something that wasn't just nucleotides in a test tube. And so he decided to work on tobacco mosaic virus, which people had worked on. They'd gotten it so pure you could get crystals of this virus. And so he did some very elegant studies with tobacco mosaic virus, and one of the important things he showed was that the RNA component of this virus, so its genetic material is RNA, not DNA. Its RNA component was a single large molecule of DNA. And he was only able to do this because of very careful preparations of this RNA. And here's this paper, used light scattering, very elegant way that, tell you the truth, I cannot understand how this actually shows it, but the referees of the paper and all the people that cited it afterwards certainly did understand it. Now, while he was working on this, there was a very fortuitous thing that happened. Max Delbruck visited from Caltech, and Max Delbruck worked with bacterial viruses called bacteriophage. And he was able to use a combination of genetics and biochemistry to start figuring out sort of the basic components of what genes are and how they work. And when he talked about his work, it just electrified Bob. It electrified him so much that he wanted to take time off and go work with Max Delbruck at Caltech in order to learn how to work with phage. And he hadn't been at Iowa State long enough to be able to go on sabbatical. And so luckily he was able to get a fellowship that I guess paid for someone to teach his classes where he could go off to Caltech. And there he worked with Delbruck on bacteriophage. When he returned to Iowa, he continued to work with tobacco mosaic virus, but he wanted to work with a small virus. And the types of viruses that they were working with at Caltech were rather large. So he searched through the literature, found what he thought were probably very small viruses, one called S13, one called Phi-X174, and he showed that it indeed was a very small virus. And he worked on methods on cultivating, isolating, and just working with this virus. And this was to set the stage for his most celebrated work after he was recruited to Caltech, which our next presenter will talk about. Jim Strauss.
I came to Caltech in 1960, 3 years after Bob showed up, as a new graduate student. The graduate class in Caltech in 1960 was very large in comparison in the past. The department was small. There were only 1, 2, 3 graduate students a year admitted. Our class was 14. Made possible by Sputnik. The launch of Sputnik by the Soviet Union gave rise to training grants in the US, and so Caltech had money for 14 new graduate students, 13 men and 1 woman. The woman was Ellen Glowacki Strauss, my wife. She was the first woman admitted to graduate study in biology through the regular admissions process, not by special considerations. And at a time when the catalog clearly said women would be admitted only under exceptional circumstances. Another member of our class was Clyde Hutchison, who will talk later about his work with Bob. Of the graduate students that year, the 14 of us, and Bob snared off quite a number of them. I was attracted to him because my undergraduate major was chemistry with a minor in math, and so Bob came to biology by the same track. And I admired his quantitative approach to biological systems. He was a pioneer in what came to be known as molecular biology, trying to understand organisms at the molecular level. And as been said, he was interested in nucleic acids, wanted to study DNA and RNA, and he had developed this system of Phi-X174 because the methods for dealing with DNA back in those days was primitive compared to what you can do today. And so he was looking for a small DNA molecule that he could handle. And he developed the FIAC system, studied its DNA, found that the DNA was a closed circle, covalently closed circle, the first demonstration of such a DNA in a living system. He measured its molecular weight, its size by light scattering and other methods, and it was about 5,400 nucleotides in size. His lab developed conditional lethal mutants of the virus so that you could define the functions of all the genes that the virus encoded. And then with the eventual sequencing of the genome in Fred Sanger's lab, of which Clyde Hutchison was an essential component, gave rise to the first completely characterized system. You knew all the sequence of the DNA, you knew all of the genes that it encoded, you knew what their function was, which was a stunning achievement at the time. Now, although most of the work in Bob's lab was DNA FIAX, RNA phage had just been described, and he wanted to study RNA as well. And so he asked me, as an incoming graduate student, to develop the system. And so I had to start from scratch, how to grow the virus, how to isolate the RNA, which was non-trivial, as has been stated, because RNases are everywhere. Trying to work how the virus infected cells, how it grew, replicated. And Bob was an ideal mentor because he was not a micromanager. He expected you to develop your own system. He expected you to learn to be a scientist. He was always there for consultation. He helped. We had weekly meetings of the group so that you could discuss your work in front of him and the other people in the group. But he did not micromanage, and it really helped me a lot because I had to make my mistakes and get there and learn to do science. In 1966, I left to join Jim Darnell's lab in New York. Jim was an RNA person. He worked with poliovirus, which is an RNA virus, and he worked with cellular RNAs, heterogeneous nuclear RNA as it was called at the time. But there again, he had developed interest in a new virus, a virus that was called Sinsheimer virus, an example of a virus that was closely related to viruses that cause a lot of human disease. And he asked me to develop the system, so I had to take the virus once again, start from scratch, learn to develop, grow the virus, isolate it, purify it, isolate the RNA, start working on its functions inside the cell. And when I returned to Caltech in 1969 as an assistant professor, I took that system with me. Now, as has been stated, Bob had become chair of the division in 1968, and so he was once again in the position to act as a mentor for me as a young assistant professor trying to learn to do what professors do at universities. And Bob's work as chair, he really was important in changing the division. He was interested in neurobiology and behavioral biology. He thought that the time had come that a place like Caltech should become more interested in that approach to living systems. And so during his tenure as chair, something like 7 new hires in that area were brought in, people who studied brain function, the function of different parts of the brain, how that affected the animal's behavior, and the behavioral biology of animals. As one example that I, as a bird watcher, find interesting was Mark Konishi, who learned how songbirds, young finches, male finches, learn to sing their song. And they have to learn to sing it perfectly or they will never attract a mate. And so he studied the brain functions that were involved in getting that to go. He also was active, obviously, in other areas of molecular biology. Tom Maniatis in recombinant DNA technology. Eric Davidson as molecular biology of developmental systems, the sea urchin. Seymour Benzer as a study of genetics of Drosophila, how that behavioral genetics of Drosophila could be examined. Bob's work as chair also was different from, the administrative structure of Caltech is different from most institutions. The administration consists of the president, the provost, and the chairs of the 6 departments, 6 divisions as we call them. And that those people meet monthly to discuss policy, to discuss hiring at the professorial level, granting of tenure, and so forth. And every month, about a week before the meeting, you get on your desk something about 6 inches high of all the paperwork that you have to go through and read and get on top of for the meeting. And I learned that because I was acting chair for 9 months of the division and learned how much work it was. So I was always amazed that Bob could do this and yet keep up the research in his group, keep it going. And also he became active nationally and internationally as well. So he was a widely active person. In 1977, he left us to go to Santa Cruz. But before he left, one of the other things I want to point out, that being so close to the administration, Bob began to make the case that biology had matured. It was time for the Caltech, which is largely known as an engineering and technology school, to pay more attention to biology and to let biology expand. And many years ago, more than 40 years ago now, Caltech decided to remain small. There was a committee that looked into this, of which I was a member. And the question is, did we want to grow, become more like an MIT, or should we remain small as a small elite institution? And the decision was made to remain small, which meant that our professorial faculty was going to be held at about 270. Biology, when we went in 1960, had about 18 or 19 biology faculty, professorial faculty. Under Bob, that started to grow. And then later chairs also made the point that biology should grow. And it's now up to something like 40 professors. But that means if the total number of professors remains constant, some other divisions are going to lose. And so you have to really be persuasive in order to get that to happen. But Bob started that and got it to happen. So Bob was an important person in his 20 years that he spent at Caltech. And the biology division at Caltech is a much better place than it would have been without him and its guiding thing. And certainly my career would have been very different without him to guide me and teach me how to do science.
Well, it's a great honor for me to be invited to represent UC Santa Cruz in honoring the life of this remarkable man. I work, my lab is in Sinsheimer Labs at UC Santa Cruz. He was, of course, our chancellor for a decade, and I've been the Robert Louis Sinsheimer Professor of Molecular Biology for the past 30 years, so I am deeply steeped in Sinsheimer in my life and career. He was a wonderful man, wonderful friend, and great chancellor. I was asked to, by Chancellor George Blumenthal, who could not be here today, to read his remarks. Chancellor Blumenthal says, "I'm sorry that I cannot be with you today to help celebrate the extraordinary life of Robert Sinsheimer. Bob, who I had the privilege to call a friend, was so many things over the course of his long life: an internationally acclaimed biologist, a scientific visionary, an educational leader, and a devoted father and husband. Foremost in the minds of many, of course, is Bob the visionary. While many people played a role in the historic push to map the human genome, it was Bob who had the audacious vision, beckoning a host of eminent biologists to our campus in 1985 to outline how the project could actually be done. Our success 15 years later not only left an indelible impression worldwide, boosting UCSC's stature, it landed us in the annals of science. But Bob impacted our campus, which he led from 1977 to 1987, in ways not as widely known. It's hard to imagine now, but there were murmurs in the mid-1970s that UC Santa Cruz might shut its doors. Applications were declining, enrollment was flat, more students were thinking about medical school and law school, and there was suddenly the sense that our innovative style of education wasn't so advantageous. Our future was anything but certain. Enter Bob. He was scholarship and academic excellence incarnate, a steady hand on the wheel when the university desperately needed credibility. And it wasn't just credibility by reputation. Bob was always engaged, never afraid to tackle entrenched problems. It took a forward-looking leader like Bob to admit that our original vision was no longer working, and that in order for us to meet our own lofty expectations, we needed to re-aggregate. And so he led us there. As chancellor, I've drawn many lessons from Bob. He demonstrated time and again that to lead, it's important first to listen. While Bob was a preeminent scientist, he also was an incredibly thoughtful campus leader. He consulted faculty. He listened to students, even when he didn't always agree with them. Another of his legacies is one he would laugh about today. Our esteemed banana slug mascot was adopted during Bob's tenure. Bob was a fan of the arguably more dignified sea lion, but an overwhelming pro-slug vote by students persuaded Bob to make the lowly but beloved banana slug UCSC's official mascot. He listened, he laughed, he led. Bob and his wife Karen left an indelible impression on our campus. They together had a vigor for life and learning, and they helped transform our university house into a hub of social and intellectual engagement. Thank you for giving me the opportunity to recognize Bob's incredible contributions to our campus. My wife Kelly and I and the entire UC Santa Cruz community extend our condolences to his family and to the many people who had the good fortune to call Bob a colleague or friend. George Blumenthal, UC Santa Cruz Chancellor. So I'll add my own comments. I first heard the name Bob Sinsheimer when I was a graduate student. The faculty in the Institute of Molecular Biology at the University of Oregon were talking about his research on the single-stranded DNA virus Phi-X174. I could sense from their tone that this was a formidable guy whose work demanded great respect. When he arrived in Santa Cruz in 1977 to take over the chancellorship, the campus was in a state of confusion over whether it was to be an undergraduate liberal arts college or a serious research university. Bob brought with him the clarity of mind and force of his own convictions that the University of California at Santa Cruz was indeed part of the University of California and would become a major research university. I listened in one afternoon in a packed Cal college dining hall when Bob actually debated UC President David Saxton over the continued existence of UCSC as a University of California campus. Armed with his characteristic logical clarity and unfazed by Saxton's patronizing view of Santa Cruz, Bob put the UC president on notice that we were a young but quite serious institution and that he should keep his hands off what we were trying to do. We never heard anything further from Saxton on this subject. And then in the mid-'80s, Bob invited the geneticist Bob Edgar, the molecular biologist Bob Ludwig, and myself to his office to discuss the surprising idea for bringing big science to Santa Cruz. His proposal was to initiate a project to obtain the DNA sequence of the 3 billion base pairs of the human genome at UCSC. We were stunned and skeptical, especially because not even a single bacterial genome, about 1,000 times smaller than our genome, had been sequenced at that time. Bob asked us to make a list of the top dozen or so experts in the world who could weigh in on the wisdom and feasibility of such a project and invite them to a conference at Santa Cruz. We set our skepticism aside and managed to persuade a stellar international group of DNA scientists to come to the now historic meeting. At the end of the day, it was agreed that first, the human genome would be sequenced. It was just a matter of when. And two, it would take on the order of 10 or 20 years and would cost about $1 a base pair, or $3 billion. When over dinner, Bob began to broach the question as to where the project would be staged, leading, of course, to his proposal that it be done at Santa Cruz. The experts had no hesitation. Oh, this would be a great project for us to carry out at MIT or Harvard or Cambridge and so on. So the conference was over. Eventually, however, as you know, the public consortium, international consortium of scientists undertook the project, which was carried out in the United States, Europe, and Japan. But then Craig Venter decided to do it in his private company so he could patent the human genome. His company appropriately named Tiger. In the late, this was all in the late 90s, and the leaders of the consortium, the public consortium, heard rumors that Venter was about to complete the sequence, announced the completion, and so they became very nervous. And at that point, the sequencing had been done, but it was all in small fragments that couldn't be linked together. And they called David Hausler at UCSC and asked him if he could help out. David Hausler was a prominent computational biologist, and he found Jim Kent, who had just received his PhD at Santa Cruz, and was a formidable programmer who had worked in Silicon Valley in the game industry. David Hausler convinced our next chancellor, Marcy Greenwood, to come up with 100 Dell workstations, which were then installed in Jim Kent's garage in downtown Santa Cruz. And he went to work night and day. They were actually, the story goes, icing down his wrists at the end of his long days, and he finally came up with the assembly of the human genome. So in the end, Bob's visionary proposal was initiated and completed at UC Santa Cruz. So I'd like to finish by saying a thank you to Bob for all he did for us and for science. And we shall miss you.
Hello, my name is Mike Mahan. I'm a professor in biology here at UC Santa Barbara. And I would just like to give you a little perspective. This will be a very short perspective of my interaction with Bob over 20 years. Those who know Bob personally, he had three loves, and three loves only. And his wife, Karen, chocolate, and cats. That's what he talked about all the time. And he was also an avid sports fan. He actually had season passes to the Dodgers every year. In fact, I was, and my family have been a beneficiary of that. He would say, "Hey, you can't make the game. Want to take your son to the game?" You know, it was really, really, really nice and generous of him. I met Bob in 1993. His lab was right next door to my office, 4 feet away. He was working on a new way to sequence DNA. I won't go into it, but it was just like this crazy thing that I would never think about. And he was just working away by himself, just smile on his face every day, just working all day long. I mean, just watching him all day. And and since he's right next door, we'd have a lot of conversations, and he started getting really interested in, molecular biology and genetics. And anyway, in 1997, I got the courage to ask him to come up and join my lab. And it's one of the best decisions I've ever made, both professionally and personally. He became really fast friends with my first graduate student, Doug Heitoff, and David Lowe, professor in biology, both of them are here today, I think. Only 2 years later, and I had little to do with it, they published a paper together in Science on a new way to make vaccines. This was in a completely different field than he was trained in. This is 2 years. Amazing. And in 2000, this same group of people, we've co-founded a biotech company called Remedyne in Santa Barbara in the basement of the Samson Research Institute. Bob was the chairman of the board, and he ran the company the right way. And it was just really comforting as a director that there was no shenanigans. It's like, this is the right way, this is not the right way. And sometimes in these quarterly meetings, it's, they want results, and they put a lot of money up. And he would just be, I would just ask, is this okay? Yes, it's okay. No, and it's fine. It was really comforting for me. And his wife kind of got screwed over, basically. We'd con her into, on the quarterly meetings, she'd have these nice dinners for us. It's a lot of dinners and a lot of work. It was great. She's an awesome cook. The wine's always flowing. She never lost her smile, but you could tell. Sorry. That she understood Bob's other love, and that was science. And I think that's what really kept them together. I mean, in 2003, after spending millions of dollars and employing about 11 people, we closed the company. But the progress we made from the company allowed us to obtain funding to now continue the work here at the university. And his commitment to the lab was unparalleled. I'll give you one story. In 2005, Bob was going to go in for a very serious medical procedure, and he invited Doug and I to come over in the afternoon. I said, sure. I thought we were coming over for lunch. And he had his lab books out on his coffee table, and he wanted to go through all the work he had done in case things didn't work out right, and he didn't want to slow the lab down. And I remember Doug, I think, yeah, there he is. We were just humbled, like, I thought I was going to have a sandwich, And I did get a sandwich, but, and I just remember that the drive home was it was hard. That's how important this stuff was to him. In 2008, he was instrumental in developing one of the first effective vaccines against salmonella for the livestock use. In 2012, he helped identify the most virulent salmonella ever reported. This was actually by screening strains from the food supply. Not good. And in 2017, in February, after 20 years working on this vaccine, it's now in clinical trials. Not done yet. 2017, June, a month after his death, he was a senior author on the last paper he had on infectious diseases. So, this is short and sweet. From bottom line, from my perspective, Bob started and finished really strong. And more importantly, it's been a privilege to work with him for 2 decades. It's an honor to call him my friend, and it's just it's just a little bit less fun than it was. But every day is better. But we miss him. We're not as good without him there, and we miss him as a team member, basically. And I'm done.
I'm Clyde Hutchison. I came to Bob Sinsheimer's lab the same time Jim Strauss did and left in 1968. It's 2 slides earlier, that one. So I made this slide and I found pictures of Bob on the web and I arranged them starting from, more formal bow ties on the left to open collar on the right. And I decided on looking at it, I should wear a bow tie and I would look younger. So I was asked by Moshe Eisenberg to say a few words about Bob's role in the inception of the Human Genome Project. And we've heard something about that already from Harry Noller, and I'll say something about it. But I wanted to put things in a little broader context to talk about Bob's legacy in a more general way and to discuss the impact of his experiments and his thinking on the direction that biology has taken and is taking as we move toward the roaring 20s of the 20th century. So, those of us who were in Bob's lab, it became clear to us that he was more than a bit of a futurist. And beginning in 1967, he began publishing essays about the future of the biological sciences. So here's something from the Bulletin of the Atomic Scientists 50 years ago, 1967. And he makes predictions that hold up very well 50 years later. He predicts the creation of life in the laboratory, the second genesis, as you see at the bottom of the top paragraph. That's something that has not actually happened yet, but we are making good incremental progress in that direction, I think. And then he showed that he was deeply concerned about the implications of these things for society. So in the bottom paragraph, I'll just read it. But before that day, as we understand life, we can control life. This has been the historical pattern in the physical sciences, and we have today a vast control over our physical environment. We will soon be acquiring a similar control of the biological world, and now the impact of science will strike straight home, for the biological world includes us. So some almost 20 years later, Bob convened the meeting that Harry talked about. The 3 people at the upper left are the organizers, Harry, Bob Edgar, and Robert Ludwig. And as far as I can tell, that list is who else was present at the meeting, and Bob, of course. So this was a movie.
We got together all the leading people in sequencing and in informatics, because you were going to have computer skills to handle all this data at the same time, to ask, would it be feasible to sequence the human genome? And we had the leading people. We had Lee Hood and John Sulston and Mike Waterston and Dave Botstein and Wally Gilbert and a number of other people. And we met for 3 days to discuss this question. I have to say, when we started out, I think most of the people were pretty skeptical, if not downright dubious. But at least they were all willing to come and talk about it. But after we did talk about it, and we thought about what might be done to improve the technology to make this possible, to think in terms of automating a lot of the process and in terms of multi-channel sequencing and so on, all of which was not available but seemed like it could be made available. The project began to seem much more feasible, at least in the minds of some of us.
So that's what Bob said. So that meeting did not directly lead to funding of what came to be called the Human Genome Project, but it did plant a seed that led some 15 years later to the first draft versions of the human genome. And here we see how the seed was recognized by the International Human Genome Sequencing Consortium in their 2001 publication in Nature. Here Bob is credited with the first proposal of the idea to sequence the human genome. But if it was the first proposal of the idea, then why is it reference 21? As academics know, the most fundamental references are listed first in the introduction. We all want to have reference 1 in a paper. So if we move on, we see that actually the first 3 references are to things done right around the turn of the 20th century, before Bob was born. But references 4 and 5 are to Phi-X 174, the system that he pioneered, as others have said. And the sequence of the genome of Phi-X 174 is the first modern thing referenced in this paper. And Sinsheimer says in his autobiography, The Strands of a Life, that he describes his research on Phi-X as the centerpiece of my scientific career. Okay, so why was Phi-X 174 the first DNA molecule to be completely sequenced? It's because it was very small, making the problem simpler, and it was the most completely characterized DNA molecule at that time. It was the first DNA molecule to be purified to homogeneity and to have its size determined. It was small, 5,386 nucleotides, as it turns out, and the purified DNA can infect specially treated E. coli cells to produce fully infectious phage particles, which shows that this molecule is the complete genome of the phage. Also, by the time the sequencing began in earnest, 8 genes had been defined by mutation, and genetic markers could be mapped onto specific restriction fragments of the genome. So Phi-X was the obvious choice for determining the DNA sequence of a genome. I think obvious to many people. Here is a figure from the 1970 edition of Lehninger's widely used biochemistry text. And it has a imaginary sequence of the genome of Phi-X 174. And it's just pretty random. It's 5,500 nucleotides long. And the caption points out that it would take about 2,000 pages like this to do the E. coli genome and about 1 million pages to do the human genome. So, you know, it was not a new idea that if you had a sequence, you could sequence the human genome. I think what was unique about the Santa Cruz meeting was they actually tried to figure out how they could do it, not just imagine that it could be done. Okay, so I was as I think Jim mentioned, I was a member of the group in Sanger's lab that actually did the sequence of Phi-X. And at the time it was going on, if some people would ask me what I was doing, I'd say, well, we're sequencing the genome of Phi-X, and they would usually say, you know, why would you want to do that? But when the actual genome was sequenced, it was obvious. Why? There are many surprises. The sequence defined 10 protein coding genes of the phage, and mutants in genes and amino acid sequences of proteins unambiguously place the genes on the sequence. And the biggest surprise was the finding that several genes overlapped another gene. Such overlapping genes produce proteins with different amino acid sequences because they're translated in different reading frames displaced by one nucleotide from each other. So FIAX showed that the DNA sequences are interesting and uniquely informative. This was not obvious beforehand. It was not obvious you would learn things that you couldn't learn from the genetics. And I like to think that the fact that the FIAX sequence turned out to be so interesting was partly responsible for the speed with which the subsequent sequencing revolution proceeded. The value added to the FIAX system by the genome sequence greatly enhanced its usefulness as a tool in developing new technology. For example, it was the material of choice for developing site-directed mutagenesis using synthetic oligonucleotides. FIAX continued and was already a major tool for the study of DNA replication in vivo and in the test tube, and it became more useful with the availability of the sequence. And here's a paper from 1967, 50 years ago. The same year, Bob wrote the prophetic essay that I started out this talk with. And this writing precedes the sequencing of FIAX by 10 years. So this paper showed unambiguously that DNA copied in the test tube by a DNA polymerase of Arthur Kornberg's was fully infectious. And the work was hailed as life in the test tube by the press, which was actually much to the amusement of many of us in Sinsheimer's lab at the time. So what we see is that much of what Bob predicted 50 years ago has come to pass. The rest seems quite plausible at this point. I skipped something here. Here is, the fact is that when it became possible to synthesize DNA based just on DNA sequence and chemicals, FIAX was still the material of choice for doing this. And this shows a plate with FIAX plaques that were came from DNA synthesized completely chemically. Okay. So much of what Bob predicted has come to pass. And in his autobiography, he says, I would love to return in a century or two to see what science, where science stands, and to learn what questions they are asking in the Sinsheimer laboratory at Santa Cruz. And so when the technology to realize this dream becomes available, he certainly deserves to be high on the waiting list.
Well, I am the final speaker today, and after I talk some about being Bob's daughter, we'll go outside and have a reception together. But I wanted to thank you all so much for coming today, and especially the speakers for helping me remember my dad, our dad. So I'm going to talk some about being his child. Microphone? Okay. You could hear me. Well, maybe this is for the videographer. I'm not sure. But I wrote a little bit about being Dad's daughter. And I'm a psychoanalyst, and when we give a paper, we read our papers. So I'm going to read the paper, and I hope you will understand. I'm just wanting to get my words as carefully as I can. As you might imagine, being Bob's daughter or child could be tricky. He could be very busy and preoccupied. An example of this comes from when I was 4 and I attended the demonstration nursery school on the Iowa State College campus. Dad didn't drive me to school often, but on the day I am recalling, he did. I noticed that he passed the turnoff to my school. I sat quietly thinking he had another route. When I realized we were approaching his lab and that we were well beyond the nursery school, I piped up. He turned, somewhat startled, to find me in the car. In his face was a moment of pleasure at seeing me, astonishment at my presence, and slight chagrin at having forgotten I was there. On the other hand, there was one time each day when we knew we would have Dad's attention. Before bed, he would read to us. I believe he selected the books, and you will soon know why I think this. He read us all of the Pooh books, but he also read us Kon-Tiki. I don't know how he came to choose the Pooh books, but he clearly was reading between the lines, as he later turned Christopher Robin and Pooh into examples for his public lecture, which he gave at Beckman Auditorium at Caltech, and it was called The Brain of Pooh. The essay was published in American Scientist in early 1971, so I presume he gave the address at least a year before. He had read Pooh to us many years prior. Pooh was a bear of very little brain. As we all know, Dad was the opposite of this, but perhaps this is why Pooh appealed to him. In his essay, Dad quotes Pooh as follows. Here is Edward Bear, that was Pooh's formal name, coming downstairs now, bump, bump, bump on the back of his head, behind Christopher Robin. It is, as far as he knows, the only way of coming downstairs. But sometimes he feels that there really is another way, if only he could stop bumping for a moment and think of it. Dad saw in these lines a splendid parable to man and his whole scientific enterprise, that we perforce go bump, bump, bump along the paths of scientific discovery, when had we but the acumen, the brain power, we could immediately deduce from the known facts the one right and inherently logical solution. This from a man who would never be described as a bear or man of very little brain. Apparently, he could imagine having even more brain power than was available to him at the height of his career. Dad wanted to find a way to go beyond what he called the limits to thought inherent in the structure of our brain, and therefore potentially extensible by genetic modification. I will take this further to say that to the end of his life, he always imagined what lay ahead in research, and apparently coming back and seeing what was done ahead. He wished that cancer research could race ahead and have prevented Karen's illness from ending her life, or that medicine would find a way to help a 97-year-old man with a 97-year-old heart from having to see his life come to an end. He seemed to think of his heart and kidney failure as problems that he could himself solve if he could only think. When we took up reading Kon-Tiki, very much his suggestion, I remember being bored beyond belief as Thor Heyerdahl led us through the details of finding funding and plotting their course. I could not believe Dad had chosen this incredibly boring book for us. I'm fairly certain that during the dull, early procedural part of the narrative, I tried to talk Dad out of the undertaking of reading the book. My parentheses is, good thing I wasn't on Heyerdahl's crew, and that Dad knew it took hard work to get to the good stuff. As soon as the crew got out to sea on the raft, everything changed, and the story became fascinating, exciting, glorious, intriguing, full of adventure. Dad, no doubt, saw parallels with his own work, paying attention to detail, having to endure the boring tedium of thorough preparation and experimentation, and then the excitement of being able to reap the rewards of undertaking an experiment to find an extremely gratifying result. Now back to Pooh. Dad ends his essay with the following. Dad was imagining a future telling us, and so perhaps when we've mutated the genes and integrated the neurons and refined the biochemistry of the brain, our descendants will come to see us rather as we see Pooh, frail and slow in logic, weak in memory, and pale in abstraction, but usually warm-hearted, generally compassionate, and on occasion possessed of innate common sense and uncommon perception, as when Pooh and Piglet walked home thoughtfully together in the golden evening and for a long time were silent. I'm going to try doing voices for the characters. We'll see how this goes. When you wake in the morning, Pooh, said Piglet at last, what's the first thing you say to yourself? What's for breakfast? Said Pooh. What do you say, Piglet? I say I wonder what's going to happen exciting today, said Piglet. Pooh nodded thoughtfully. It's the same thing, he said. Dad had another quote about the excitement of anticipation that I think came more to the point. I would like to end my talk with this quote from A.A. Milne that Dad actually put in the middle of his article. I see this as a better ending point for us today, because those of us here still have more of our lives to live and enjoy. It is an observation about pleasure. Christopher Robin asks Pooh, and I don't know what Christopher's voice sounds like, maybe you guys do. What do you like doing best in the morning? What do you like doing best in the world, Pooh? Well, said Pooh, what I like best. And then he had to stop and think, because although eating honey was a very good thing to do, there was a moment just before you began to eat it which was better than when you were. But he did not know what that was called. Here is to our having more such moments in our lives, and at times when we are full of the pleasure of anticipation, we could think of Pooh and of Dad having had many such moments in their very rich lives.